Hubble has now been in space for over 33 years, and its mission has been a resounding success. It was never designed to look at objects in our solar system, but that hasn't stopped it from actually doing so over the course of its mission, and as a result, it has captured some very special moments we would have otherwise missed. Not every planet has its own dedicated mission. Plus, there is a lot to see besides just planets in our solar system. So, let's take a journey through our solar system. From here to the very outer reaches, looking at some objects you've probably never even heard of as we explore what exactly Hubble has seen in our cosmic back garden. I'm Alex McColgan and you're watching Astrum, and in this episode of the Hubble Images series, we'll look at some Hubble snapshots of our solar system, and I'll give you a context and an explanation of the special moments it's captured. Let's begin our grand tour of our solar system right in our own backyard, with our immediate neighbour, the Moon. Now, the Moon has a very big apparent diameter in our sky, which means Hubble can't fit the whole thing in one go. Also, there are other missions out there which capture far better images of the Moon, like NASA's Lunar Reconnaissance Orbiter for instance, so Hubble's time is better spent looking elsewhere. However, this image was taken in 2012, just as Venus was passing in front of the Sun. So why image the Moon? Scientists are using the Moon as a giant mirror to search for slight variations caused by sunlight being scattered through Venus's atmosphere. These variations allow scientists to determine the chemical composition of the atmosphere. Now, we already know the composition of Venus's atmosphere, which means this was just a test to see if the light scattering experiment produces accurate results. You see, Hubble often looks at distant stars when an exoplanet is transiting in front of it, and it uses this process to determine the composition of that exoplanet's atmosphere. The Sun is too bright for Hubble to look at directly, so light reflected off the Moon provides the results scientists were looking for. Hubble might struggle to fit the Moon in one go, but this is less of a problem for our next planet, Mars. Mars is often imaged by Hubble, giving us a full view of the entire disk, which can't always be seen by orbiting spacecraft. In these images, Hubble can spot dust storms, seasonal variations and other weather phenomena, important information to have for any rovers on the surface, and to build up a catalogue of information which can be used to better predict the weather in the future. This time-lapse shows a planet-wide dust storm, obscuring most of the surface features from view. However, you'll also notice Mars's two moons, Phobos and Deimos, whizzing around the planet in the background. And they really are whizzing. Look how far they travel in just 42 minutes this time-lapse shows. Another time-lapse shows Phobos, Mars's closest and largest moon, move over the course of 22 minutes. Phobos orbits the entire planet in only 7.5 hours, meaning it is the only moon in the solar system to orbit quicker than a day on the parent planet. Stepping past the last of the inner planets before we arrive at the first of the gas giants, there is a barrier to cross, the asteroid belt. Still, this region is filled with fascinating objects for Hubble to study, such as the misleading asteroid 6478 Gold. It may surprise you to hear that this is an asteroid, when it clearly looks like a comet. It's even got two tails like we are used to seeing on a comet. But no, this is in fact an asteroid found in the asteroid belt, imaged in 2019. So, what's with the tail? Well, it is believed that this 3.5 kilometer wide asteroid has been steadily speeding up its rotation due to something called the Yorp effect. Radiation from the Sun has a slight pushing effect, meaning when it acts on an irregularly shaped body, under the right conditions, it can cause the body to speed up its rotation. Asteroid Gault's rotation has gradually sped up until it now rotates once every 2 hours, right on the limit of what an asteroid can handle. loose matter is being ejected into space by centrifugal forces, which are now overcoming the gravity of the asteroid. Eventually, this asteroid will disintegrate altogether, as most asteroids and comets are not solid rocks, but more like rubble piles. With somewhere between 1 and 2 million asteroids larger than a kilometer in this region, and millions of smaller ones, the asteroid belt is a chaotic place. To show you what I mean, let's examine P/2010 A2. This looks like a pretty standard comet, wouldn't you agree? Having a close-up look at the nucleus though, what is this weird filamentary structure? Surprisingly, this isn't the shape of the comet's nucleus. Again, this isn't even a comet. What you are looking at here is an extremely rare event. It is two asteroids colliding. This X-shape near the nucleus is in fact streamers from the impact, rubble being flung into space in 4 directions, slowly being pulled back in towards the center of mass by the extremely weak gravity, with particles in the tail here having escaped the gravity well altogether. Beyond this small chaos, asteroids in the belt remain on fairly stable circular orbits around the Sun. If they were to stray from this path, as comets do, they would start having to worry about a much larger source of gravity: Jupiter. Jupiter is sometimes referred to as the solar system's vacuum cleaner, and for good reason too. Jupiter by itself is so massive, it makes up almost 3/4 of all the mass in the solar system, excluding the Sun. As a result, it has a powerful gravitational effect on nearby objects. This was particularly evident when the 2-kilometer wide comet Shoemaker-Levy passed too close to the gas giant in 1994. Jupiter's gravity not only pulled the comet in, it also ripped it apart, meaning by the time Shoemaker-Levy impacted Jupiter, it was already in several different fragments. This was the first direct observation of an extraterrestrial collision. Interestingly, Shoemaker-Levy had been captured by Jupiter around 20 years previously, but up until this point it was orbiting Jupiter as an active comet. Again, the first time this had been observed. However, this orbit took it too close to Jupiter's surface where tidal forces pulled it apart, and only a year later these fragments impacted Jupiter at 60 kilometers a second, or 210,000 kilometers per hour. The impacts caused fireballs over 23,000 degrees Celsius, which rose 3,000 kilometers above the limb of the planet. The largest impact left a dark spot on Jupiter over 12,000 kilometers across, about the size of Earth, and the impact was estimated to have released energy equivalent to 6 million megatons of TNT, or over 600 times the world's entire nuclear arsenal put together. Various impacts, while perhaps not as impressive, have been imaged since, and give weight to the theory of Jupiter being a cosmic vacuum cleaner, protecting the inner solar system planets from devastating collisions. Beyond its destructively powerful gravity, Jupiter has other sights for Hubble to see that are a little more on the ethereal side. You see, Earth isn't the only planet to experience auroras. While you can see aurora with your naked eye on Earth, auroras are actually brightest in the ultraviolet. As I mentioned before, Hubble can detect ultraviolet light, meaning we can closely observe this phenomenon on other planets too. Jupiter's is the easiest to spot. It's the biggest and closest of our neighboring gas giants, and its powerful magnetic field and strong radiation produce a bright aurora. In 2016, the Juno spacecraft was on its way to Jupiter, which provided scientists with a unique opportunity to measure solar wind on its way to Jupiter with the Juno spacecraft, and observed subsequent changes in the aurora with Hubble. As a result, Hubble observed Jupiter almost every day for several months. What Hubble found out was that these auroras are hundreds of times more powerful than on Earth, with a radiant power of 100 terawatts. But also surprisingly, they never cease. On Earth, aurora light up around the poles during a solar storm. This implies that auroras on Jupiter are not just powered by the solar wind.
Since Juno has arrived at Jupiter, the data it has collected suggests that the auroras are mainly powered by charged particles in Jupiter's fierce radiation belt, which feed into the planet's atmosphere via its magnetic field lines. The magnetic field has also been found to produce alternating currents rather than direct currents. This accounts for the radiant energy of the aurora, which would be impossible if energy was transferred through the magnetic field via direct currents.
We've spent a lot of time with Jupiter, but let's take the time to examine a very special one of its moons, Europa. After all, this may be the home of our closest living neighbours, and Hubble has captured images of it in surprisingly high detail considering the distances involved.
For those of you that don't know, Europa is a large moon of Jupiter and is one of the most promising candidates for life in the solar system. We aren't expecting to find anything on the surface, but rather underneath, in an ocean of liquid water. Europa is an icy world, and being this close to Jupiter produces extreme tidal flexing. The theory goes that energy produced from tidal flexing keeps the underground ocean warm enough for it to remain liquid. Various missions have since been looking for evidence of this ocean. Surprisingly, Hubble has been very useful in this endeavour. Galileo and the Voyagers were able to produce much higher resolution images of Europa compared to Hubble because they passed the moon by reasonably closely. However, these missions were not able to observe the ultraviolet. With this ability, Hubble has spotted possible plumes of water erupting on Europa's surface. Volcanic activity would imply that the interior mantle of Europa is liquid, and because it must be water, this suggests the ocean theory is correct. Since the first observation, lots more plumes have been detected. Hubble's vision was utilized again to detect salts on Europa's surface. Most missions use infrared to examine a planet's surface, as most of the interesting emission bands of substances are found in the infrared. However, sodium chloride, or salts similar to those found in our oceans, are mainly visible in the visible light spectrum, which means these salts on the surface of Europa were undetected by Galileo. Hubble, viewing in the visible light spectrum, confirmed that sodium chloride is found all over the surface of Europa, likely having originated from the underground ocean and then carried up in the plumes to be deposited on the surface. The exciting prospect about an ocean of sea salt is that it indicates the ocean floor could be hydrothermally active. These thermal vents on Earth can be a hive of life, so scientists are excited to investigate this further, although sadly, we may still be a few decades from having a submarine mission to check this out.
Let's continue our tour. There are other gaseous planets to explore, and for our next image, Hubble turns its gaze away from Jupiter and on to Saturn.
Since Cassini ended its mission in 2017, Saturn has been without a dedicated mission. This means the best view we now have of Saturn is courtesy of the Hubble Space Telescope. Hubble is often observing Saturn, checking for various phenomena. Hubble can monitor the weather on Saturn, giving us a better understanding of seasonal variations in the atmosphere. Cassini was only around Saturn for half a Saturnian year, meaning Hubble is now filling in the remaining data as best as it can. The most notable events Hubble witnesses are huge storms which span across thousands of kilometers on the planet. But because the Saturn system is such a beautiful place, all the data collection also provides some striking shots. Here are a few of my favorites.
We're reaching the end of our tour now with just a few planets left to visit. As we've travelled out from Earth, Hubble has captured more and more distant objects, which, if it hadn't been for this space telescope, would have been increasingly hard to study. Now we have finally arrived at the first of the icy giants, Uranus.
Much like Jupiter and Neptune, Uranus has also had Hubble observe storms on its surface, and even had aurora detected around its magnetic poles, which apparently do not line up with the rotational axis at all. Uranus's rotational axis is already pretty weird, appearing to be on its side compared to the rest of the planets in our solar system. This means that at some points in Uranus's year, it appears to roll along its orbit. It also means that it hardly ever experiences a solar eclipse from its moons. 2006 was the first opportunity we had to witness this event, as the last time the moons were aligned correctly was in 1965, before telescope technology was good enough to see a satellite transit on an object so far away. Hubble not only saw Ariel's shadow crossing over Uranus's surface, but also a complete view of Uranus's bands. Since this equinox view, through Hubble observations of Uranus over a section of its lengthy 84-year orbit, we have also been able to see seasonal variations develop in the atmosphere. As a pole becomes more exposed to the sun, the atmosphere seems to get lighter in colour. This is believed to be a large cloud cap that forms during that hemisphere's summer, and it is expected to dissipate again as Uranus heads back towards its year's equinox. As Hubble is only 33 years old, it hasn't even been able to see half a year on Uranus, so there's still a lot to learn about its seasons yet. One object that we would have never even known about if it wasn't for Hubble is the smallest moon of Neptune, Hippocamp. The outer ice giants, Neptune and Uranus, have largely been forgotten by space agencies around the world, only ever having one flyby in 1989 by NASA's Voyager 2 probe. This means that our knowledge about these massive worlds is pretty limited, and it would be more limited still were it not for Hubble observing them from time to time. One of the major discoveries Hubble made about Neptune was the discovery of a new moon in 2013, which has now been named Hippocamp. Now, Hubble has discovered many moons in its time, especially around Jupiter and Saturn, but what makes Hippocamp special is that it could well be a fragment from the much larger moon of Neptune, Proteus. The 400-kilometer wide moon does indeed look like it had a tumultuous past, with giant impact craters 50 to 100 kilometers in diameter. One of these collisions likely fragmented parts of Proteus, which then fell into orbit around Neptune. Hippocamp is probably the biggest fragment, as it's an irregular 35-kilometer long object, and orbits fairly closely to the larger Proteus. As our penultimate destination, let's move on to Neptune itself. As I mentioned before, Hubble was never really designed to monitor our solar system. However, in 2015 it was decided to dedicate more of Hubble's time to the outer ice giants, having roughly one observation per year. This has meant that we can better monitor seasonal changes in those planets' atmospheres. One of the most noticeable of these changes are the giant storms spanning thousands of kilometers. Voyager 2 saw one such storm as it passed Neptune back in 1989, which was later dubbed the Great Dark Spot, comparable to Jupiter's Great Red Spot. However, unlike Jupiter's storm, the one on Neptune has since disappeared altogether. Other storms have come and gone, and the latest one was seen in 2018. It lasted a few years, but it too is now believed to have disappeared. While there is not enough data to speculate how these vortices develop, it could be that Neptune is like Jupiter with bands in the atmosphere. While they won't be as defined or as many as there are on Jupiter, the bands on Neptune would travel at different speeds. This could cause vortices to appear where the bands meet. Once the storm has got going, it can drift around the planet, even between the bands. But once it leaves its power source, it begins to slowly diminish, which is what we have seen. Interestingly, Hubble is the only program that can monitor these weather changes, as in most light wavelengths they are very hard to spot. Hubble, though, can probe Neptune and Uranus in the ultraviolet. By this point, you might recognize that we've run out of planets, so our tour must come to an end. But perhaps before we conclude, there is one last dwarf planet that bears looking at, beyond Neptune, that has been the target of Hubble's study. I'm sure you all know it.
I am, of course, referring to 2007 OR10, or Gonggong. Huh? Which dwarf planet did you think I meant?
You would be forgiven if you have never heard of this object before, even if it is the third biggest dwarf planet in our solar system, third only to Pluto and Eris. And like them, this dwarf planet is also found billions of kilometers away in the Kuiper belt. While this object was not discovered by Hubble, Hubble did find out that it had a moon. It was not discovered by the original investigator as it was very faint in the images. However, recently a research team had a suspicion that 2007 OR10 could have a moon as it has a slow rotation, about 45 hours. Most Kuiper belt objects rotate in under 24 hours. It was hypothesized that a moon's gravitational tug may have slowed it down, and after searching some archival Hubble data, it proved to be so. This discovery means that nearly all the dwarf planets in the Kuiper belt have now been found to have their own moons. This could be because out in the Kuiper belt, objects move pretty slowly. This means that if there ever were collisions between objects, then fragments would have stayed in orbit around the body rather than escaping the object's gravity. This could be why asteroids in the asteroid belt don't tend to have moons. Collisions there are a lot more energetic, meaning debris just shoots off into space. Finding the moon around 2007 OR10 means that we can have better constraints on our solar system formation models, so useful data indeed. You can see from just these images how important Hubble has been to humanity's knowledge about space and our solar system, and it has done far more than just this over the course of the last 30 or so years. Hubble may well be the most important space mission to date, expanding our horizons and providing data that will be utilized for many years to come. And given that it might last until 2040, it might even outlive its spiritual successor, the James Webb Space Telescope, which was launched in December 2021, but is only expected to last for around a decade. Of course, the James Webb Space Telescope is eager to make up for its potentially shorter lifespan, and has already started turning its gaze to some of the same planets Hubble has imaged. I can't help but be captivated by this image of Jupiter, captured in the Webb's NIR cam. The fact that the Webb primarily captures light in the infrared range means that its images have an ethereal beauty all of their own. You can see here in stunning detail the haze of auroras on Jupiter's north and south poles, or here in this image, detailed images of Jupiter's rings. Yes, it has those, as discovered by Voyager 1 in 1979. I find this image of Neptune equally entrancing, seeing how tiny it looks in the vastness of space, and then realizing that this is an entire planet, captured in incredible resolution, really strikes home at the power that the James Webb Space Telescope brings to bear. These images have caught some of the faintest rings of Neptune that haven't been imaged in nearly 3 decades since Voyager 2 flew past. This is also the first time the rings have been seen in infrared, giving scientists much to learn about them and the stormy planet they surround. The Webb has even taken a cool image of Saturn, whose rings shine brightly against the darker planet. This is a little misleading though. Methane gas in Saturn's atmosphere absorbs almost all the infrared radiation coming in from the sun, making it appear darker. Meanwhile, the icy rings are much less absorbent, making them glow as you see here. Ultimately, however, there is no contest between Hubble and the Webb, as the two are not directly competing. Given the differences in the spectrums of light they are able to detect, the Webb can't ever provide what Hubble can, a clear picture of what these planets might look like to an unaided human eye. Similarly, Hubble can't detect all the bandwidths of radiation that the Webb is able to see. They each have their niche, and they each advance our scientific understanding. I am excited for what the James Webb Space Telescope will bring, but this is definitely a good time to appreciate Hubble's accomplishments, and I look forward to what the future will bring for it too. Thanks for watching. If you want to see more of what Hubble has done, I recommend checking out my Hubble playlist here. A big thanks to my patrons and members for your support.
If you want your name proudly placed at the end of every single Astrum video too, check the links below. All the best and see you next time.